Unit 4, folks. We are all about functions in this unit. In lesson 1 of this unit, we're going to be talking about describing and graphing situations, right? So we're not to the function part yet, but we're going to be talking about situations. And describing and graphing is pretty challenging. What we hope to accomplish by the end of this is to be able to explain the relationship between two quantities and if they are a function. Then you want to be able to identify independent and dependent variables and use words and graphs to represent them. And then you can make sense of descriptions and graphs of functions and explain what they tell us about situations. So go ahead and get this into your notes. And now for my favorite conversation, bagels, specifically fresh bagels. Boy, do I love a fresh bagel. In fact, if my eyes don't fail me, I think that is a cheddar bagel. Anyway, we have a customer at a bagel shop and is buying 13 bagels, right? Or as they say, a baker's dozen. And the shopkeeper says that it's going to be $16.25. Jada, Priya, and Han, who are in the shop, all think that this is a mistake, right? Jada says to her friends, shouldn't the total be $13.25, right? So she's asking. Priya says, I think it should be 13. Han says, no, I think it should be $11.25. So here we have 1, 2, 3, 4 different perspectives on how much 13 bagels should cost. What do you think? What do you think the cost should be? Well, obviously, as we take a look over here, we see that one bagel is $1.25. So if you buy 2 bagels, I guess that's 2 of those. So that's going to be $2.50. And as you go down, it's adding another $3.75. 4 bagels should be $5. That's a 5. And then another one, $6.25, $7.50, $8.75, $10, right, for 8 bagels. And we got $11.25 and $12.50 and $13.75 and $15 and $16.25, right? So isn't the shopkeeper right? Argue with me. Say, hang on, pal. You're trying to pull a fast one right now. I don't think that it should be that amount. Why not? Well, there's a discount. If you buy 12 bagels, isn't that $10? So shouldn't 12 bagels be $10? And it says, shouldn't 9 bagels be $8? So shouldn't that be $8? And shouldn't 6 bagels be $6? So did I add wrong? No. It's just that there's a different way of getting to the best cost. So there's an overall best cost. The best cost for one bagel is $1.25. There's no way around that. And in fact, all the way through 5 bagels, there's really no way around it. In fact, if you're going to buy 5 bagels, you may as well just buy a half dozen. Why? Because as you see here, 5 bagels is going to cost us $6.25. And if you buy a half dozen, you could save yourself 25 cents and gain an extra bagel. Let's take a more sort of two-way table approach, right? Or a table approach and then a graphical approach. So let's look at this in another fashion. So we got the shopkeeper's price, right? So no matter what, we have our count of bagels, right? This is the number of bagels. As we look at the shopkeeper, obviously the shopkeeper is going by the add $1.25 as we go down the list, yielding 13 bagels of $16.25. Now, to understand Jada's principle here, we needed the sign, right? So we start with, Jada just goes right to the 6 bagels for $6. Then she adds $1.25, $1.25, $1.25, all the way till she gets to 12. A dozen bagels, $12. How does Jada go from $12.25 to $12? Because she just gets 2 loads of half dozen bagels for $6. Then she adds $1.25, which is another way to save some money, but I don't think the best way. Priya starts off with the $9 bargain for $8, and then adds $1.25 to get to $9.25, another $1.25 to $10.50, another $1.25 to get to $11.75, and yet one more $1.25 to get to $13. So a little bit better than Jada's version. Han, I think, has got this down to a science, right? Hans says, hey, how about just the dozen bagels for $10 plus the extra singleton for $1.25 to get to $11.25. So I think that's the best price for 13 bagels. How about if you look down the line for 12 bagels? What's the best price? Right here. So best price, best price. Okay. So now let's start thinking about the best price version of this. $1.25. The best way to buy, the best possible way to pay for 5 bagels is just by $1.25. So all the way from here to here, we're going to add $1.25. Right? We're going to add that in. But once you get to the half dozen, the best price is straight up $6, right? That's the half dozen deal. Then to go from there to 8, the only way you can do that is to add $1.25 each time. But then this is another 9 bagel deal. So that's the best price to get for 9. Then keep adding $1.25. And then this is a deal for the dozen. And then this is just add $1.25. So again, in real life, there's different ways to strike best price. But there is only one way to arrive at a best price for each particular number of bagels. So if you wanted to buy 10 bagels, the best way to pay for that is to buy the 9 bagel deal and then add 1. The best way to yield 7 bagels in the most cost conscientious fashion is to buy the half dozen deal and then add $1.25. The best way to get 3 bagels is just to pay for $3 $1.25s in a row. Okay, so that being said, let's move on. I said we were going to look at this both in a table format and graphically. So here graphically is the way this goes, right? So the blue represents the adding $1.25 over and over again. And it's just one continuous, nice linear function, right? Now the best deal all the way up until 5 is just to do that version. That's the best way. But then the green represents buying a half dozen bagels and then adding $1.25. Fine. So this is the best deal. Add $1.25, add $1.25. But then the best way to buy 9 is just to use the deal. Then add $1.25, $1.25. But then the best deal for 12 is to buy the deal and then there. So this idea of best sort of doesn't fit a clean function look. And by that I mean we would go like up like this, and then when we get to 6 we would divert down. Up here, down to 9. Up here, down to 12, up to 13. And so if you want to take a better version of that, take a look at it, here we are. Right? So best price on the y-axis, number of bagels on the x-axis, and you'll notice that 6 bagels actually costs less, right, $6 than the 5. Same with the $9, or 9 bagels. Costs less than if you bought 8. Right? So just interesting to look at this in a graphical fashion. The key is to slow down and to think. And again, this is a hard thing for Americans. I think it's why we fail in the educational system, right? Our value system doesn't value going slow and thinking, right? We want it fast. We want to get things cheap. You got to slow it down. You got to think. When you slow down and think, you will operate at a level superior than those around you, which helps secure yourself a better future. Just saying. I had to slip that in. Our next conversation has to do with a dog on a leash. 3 days in a row, a dog's owner tied his dog's 5-foot leash, right? So the leash is 5 feet long. And he ties the leash to a post outside a store while he runs into the store to get a drink. Each time the owner returns within minutes. So it looks like our time is 160 seconds. So if you divide 160 by 60, it's like 2 2/3 minutes, right? So the 2-minute mark would be there. So 180 seconds would be the official 3-minute mark. So it's less than 3 minutes. Okay, so he's not a unruly dog owner. And so let's take a look at sort of an example of what could have happened while the owner was in the store. Now, time in seconds is the X value. The Y value is the distance from the post that the dog is, right? So how far is the dog from the post? Now think about this. The dog could walk to the post, away from the post, to the post, away from the post. The furthest the dog can get away is 5 feet because it's a 5-foot leash, right? And where does the dog start? At time 0, it looks like the dog is about 1.5 feet from the post. That's his distance initially. And as soon as the owner walks away, the dog goes all the way in just a couple of seconds to 5 feet. My guess, he's walking with the owner towards the store, and then the leash gets taut. Then, as time goes on, the dog walks back towards the post, but he's still pretty far out on the leash at 4 feet. Then as time goes on, the dog gets closer to the post to where he's less than a foot away after that 2 and change minutes. And that's the story that we see in that picture. So again, as this line goes down, time is increasing, but the distance from the dog to the post is getting shorter. Okay? This is not uphill or downhill. This is distance going back and forth. So it says that the owner does this for 3 days in a row. It's a 5-foot leash. And the dog's movement each day is described here. So on day 1, the dog walked around the entire time while it's waiting for its owner, right? So that means that there's no sort of set distance that happened, right? The distance is constantly in flux because the dog is walking around the entire time. On day 2, the dog walked around for the first minute and then lays down after until the owner returned, right? So the dog walks around for a minute, and then the rest of the time, the distance is remaining unchanged. Number 1, distance constantly changing. Changing. And number 2, after 1 minute, the distance stays constant. Okay? And then on day 3, the dog tried to follow its owner into the store, but was stopped by the leash, right? So at that 5-foot mark, then it started walking around the post in one direction until the leash was completely wound up around the post. So this means that the distance is getting shorter, 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 and shorter pretty consistently until it's 0 feet from the post because it's totally tangled up around the post. Horrible, I know, but that's the case. So our mission, should we choose to accept it, and we will, is to make a graph 3 times. Right? So you're going to make this graph 3 times, but each time has to do with the day conditions that surround it. So day 1, the dog walked around the entire time while waiting. And each day, right? Each day, these 2 things happen every time. Each day, the dog was initially 1.5 feet away from the post when the owner left. So that means that every graph is going to start with a dot right here, right? This dot happens every time. And then each day, 60 seconds after the dog's owner left, the dog was 4 feet from the post. So at 60 seconds, right? 60 seconds, we're going to be at 4 feet. So we know that at that 60-second mark, the dog had to be right there. Okay. Everything else is up to the description of the day. So for day 1, the dog walked around the entire time while waiting for its owner. Okay, so I guess we could say, well, after the owner immediately left, we could say the dog tried to go all the way to here and then went something like this, and then that's it, right? That dog is walking around the entire time, and he's getting closer, right? That's one version. I want to give you an alternate option, right? Or the dog did something like this, paste, 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 and then something like that. The dog could walk if this is the post and the store is over here, right? The dog could walk, hit the tight point, come back and forth, right? And just keep pacing back and forth. Or the dog could just go and sit right down by the post. But it said that he was walking around the entire time. So I think that this is a good scenario. Again, at any given moment, if the dog's walking around, the distance is constantly changing. At 80 seconds, the dog is about 3.5 feet away. At 140 seconds, he's about a foot away. At 120 seconds, about 3 feet away. At 20 seconds, he's about 5 feet away. All makes sense. Okay. And this is on day 1. Okay, now you're going to need to make a new graph because we're going to do day 2. Now I know the instructions say that you're just going to do 1, but this was as if we were in school and we were working on this in different groups and then posting all our answers together to learn from each other. Since we're working on our own, we're going to do all 3. So on day 2, again, each day, 60 seconds after, the dog's 4 feet from the post, so it's 60-second mark, and the dog always starts 1.5 feet away. Okay, the dog walked around for the first minute and then laid down until its owner returned. So maybe the dog starts walking towards the store, then the guy turns around and says, hey, go back and go sit down. Or then the dog gets to the 60-second mark. At 60 seconds, we have to get to that point. Okay, and then what? It says he walked around for the first minute. At the first minute is that 60-second mark. Then the dog just laid down until the owner returned. So he lays down. His distance remains unchanged. That means straight line. Straight line means no change in distance, right? Remains at 4 feet away. At 60 seconds, the dog has to be 4 feet, which is 1 minute. So the dog stays at the 4-foot mark. This is day 2. One other option for day 2 is just to think, well, the dog could have initially walked closer to the post and then towards the store and then stayed on that, right? Or the dog could have tried to hit the end of the leash and then back down and lay down. And so this part is non-negotiable, but this area here is totally up to the reader's interpretation, right? Has to start at 1.5 feet away, walks around. What does that mean? It could mean got closer to the post, further from the post, closer and further from the post, either way, or I should say further and closer. Interpretation up to the reader. So for day 3, what I'd like for you to do is to do this one on your own, right? The dog tries to follow its owner into the store, but was stopped by the leash. What does that mean, right? And remember, dog has to start at 1.5 feet away, and at 60 seconds has to be 4 feet away. So the dog tries to follow its owner into the store, then gets stopped by the leash, then starts walking around the post in one direction, which means the leash has to keep getting shorter and shorter and shorter until it is completely wrapped up around the post. So that's 0 feet away from the post until the owner returned. And let's just say that the owner is going to return at 166 seconds. All right, so let's see what you can do with that one in your notes. Now let's take the discussion about a function a little bit further. Below you'll find 2 pairs of quantities from a situation you've seen in this lesson, right? Each pair has a relationship that can be defined as a function, right? So time in seconds, right? So time is the variable, seconds is the unit, since the dog owner left, and the total number of times, right? So the number of times the dog has barked, right? So we have these 2 ideas. Then you have time, again, in seconds, since the owner left, and the total distance in feet the dog has walked while waiting. So again, not the distance from the pole anymore, but the total distance the dog walked. So if the dog walked left, or I should say right 3 feet, and then left 3 feet, the dog has walked a total of 6 feet, not 0 feet. So let's choose a pair. Let's first start with this concept, time and total distance, right? In that function, which variable is independent? That means like which variable seems to not really depend on the other one. I think time really kind of marches on, right? So time, I would say, is the independent variable, which by default makes total distance the dependent variable. So in sentence form, we will say that total distance is a function of time, meaning that distance depends on the time. Let's double back. Time in seconds and number of times the dog is barked. I believe that time, again, would be the independent, and the number of barks would be the dependent, right? The longer we go on, the more barks there are. The shorter time, the fewer barks. But barks is going to be dependent on how much time has elapsed. So number of barks is a function of time. And these are ditto marks. So working off the total distance and time relationship, right? Let's get a scale on the axis and then explain our reasoning, right? So time is in seconds. So I think we went to 160 seconds, right? So this is going to be time in seconds. And I think we went 20, 40, 60, 80, 100, 120, 140. I think that was about the scale of things. And now the total distance, right? So say the dog just keeps walking. I think maybe like a steady pace, and then maybe the dog a steep pace, and then the dog maybe just didn't do anything for a few seconds, and then the dog walked further, and then the dog stopped for a second, and then the dog walked further. And eventually, what happens here? So let's just say that this is, 5, 10, 15, 20, 25, 30. If the leash was 5 feet long, in a few minutes, it's not impossible that the dog walked 6 lengths of leash, right? So this is distance in feet, right? And this is time in seconds. And so to discuss this, we want to say, well, listen, at 0 time, the dog hadn't walked any feet. And then after 20 seconds, the dog had gone 5 feet. Maybe after another 35 seconds, the dog had gone an additional 5 feet for a total of 10 feet. But at any given point, the total distance is a function of time. So at 120 seconds here, the dog had walked a total of 20 feet. At 160 seconds, the dog had walked 30 feet. Let's try this with the bark and time. Okay, so we're going to use the same units across the bottom, time in seconds. And then over here, number of barks. And again, I don't know, let's not make the dog too obnoxious. So at 0 seconds, the dog hadn't barked yet. And let's say at first the dog barked, a bunch of times, right? Like the dog was really sad. So in the first 20 to 40 seconds, let's just say that the dog barked, I don't know, we'll say 5, 10, 15, 20, 25, and we'll go 30 times again, a scale of 5 over here. So the dog barks for 10 barks, 40 seconds, and then the dog just kind of doesn't say anything. And then right at the end there, the dog sees the person checking out and begins to bark again for the owner, and until the owner gets there, right? So for a grand total of 15 barks, right? But how many times did the dog bark here? None. The dog was quiet. How do I know? No increase in the number of barks throughout that duration. The dog barked for 140 to 160 seconds and from the first 40 seconds, right? And how do I know that's where it barked? Because there was an increase in the slope, which was an increase in the number of barks. So pretty straightforward situation here, right? The relationship between two quantities is a function if there's exactly, right? And this is sort of a review, exactly one output for each input. We call the input the independent variable. So the input is the independent variable. And then we call the output the dependent variable. So let's take a look at a relationship between the amount of time since the plane takes off in seconds and the plane's height above the ground in feet. Now think about that. When the plane first takes off, the plane is looking to get to cruising height, and then it sort of stays at that point. But in the first few seconds since the plane takes off, if you've ever flown, it's really just, you could even see it in the plane. You're really leaned back, right? So these two quantities form a function, right, of if time is the independent variable and the height is the dependent variable or the output. And this is because, again, any amount of time since the plane takes off can be only one height at any given moment, right? So it can't be at two different heights at the same time. That's why it's a function. It will only have exactly one output for each input. So the first 50 seconds, we could take a look, right? After 50 seconds, the plane might have a height of 180 feet. And it cannot be simultaneously 180 feet and 95 feet off the ground at that 50-second moment, right? So it will only maintain one output. For any input, there's only one possible output. Now, if you had flipped these around, right, if we considered height as the input and time is the output, this would not be, right? This would not form a function. Why? Because at some height, it could be at the same time. So you would have a dot above a dot, right? Something like this. And that would fail the vertical line test. So that would be no dice. So say like when the plane is 1,500 feet above the ground as an input, right? At 1,500, that could happen at 300 seconds, 425 seconds, 275 seconds. It could be at that height for quite some time. And so that would be a problem. It would have three different times at one particular height. So it doesn't work when height is the input. Time as the independent variable will allow this to be a function, right? So for any input, multiple outputs means that it wouldn't be a function, right? Not a function. To be a function, exactly one output for each input. It needs to pass the vertical line test, not fail the vertical line test. Okay. So this is what that kind of looks like. Time in seconds as the independent, height in feet as the dependent. And what do we have? On the ground, plane lifts off. First 50 seconds, it's going up pretty steadily. Then it really gathers some height over that period of time, right? The slope increases, right? So we start to sort of steepen our ascent until we get to cruising altitude of about 1,500 feet. The point 125, 400, so somewhere right here and about here, that moment, 125 tells us that after 125 seconds is taken off, the height of the plane is at 400 feet. So back to our learning targets, we can explain when something is a function. We spent a lot of time right there at the end, and we talked a little bit there at the end about independent and dependent, and we can make sense of descriptions and graphs of functions, right? So what we did is we took descriptions and made the graph. At the end with the plane, we took a look at the graph and we gave a description of what's going on. So that fluency of going back and forth will be important. At the end of your notes, please place a gigantic star so that I know you listened all the way to the very end.